Compared to the awake brain, you might think of the anesthetized brain as a simple, predictable system whose activity is stationary on a long time scale, but at relatively light doses, this is not the case. Presented here is a set of time-frequency spectrograms based on local field potential recorded from 5 brain regions in a rat as the dose of isoflurane was periodically lowered. Below 1.75%, we can see that there are about 3 discrete modes of oscillatory activity that each region spontaneously and abruptly switches between. Furthermore, the state transitions appear somewhat synchronized between the 5 regions. When the authors ran PCA on the concatenated power over time of all regions at all frequencies, they found that only 6 components were needed to account for 80% of the variance. In other words, the overall state of activity in these regions was low-dimensional. Furthermore, in the subspace band with the first 3 PCs, clustering revealed just 8 characteristic activity states. The sparse network of states and structured transitions between them is theorized to be critical for ensuring the brain consistently returns to the awake state. While this analysis strongly suggests that synchrony between pairs of individual brain regions produces low-dimensional global dynamics in the anesthetized state, the consistency and strength of the synchrony has not yet been directly characterized. In the present study, we aim to evaluate the consistency of oscillatory state relationships between recording sites and the synchrony of spontaneous transitions between them at constant anesthetic dose. We recorded LFP from 7 rats using linear silicon probes inserted into 2 cortical regions, either right V1 into M1 or right and left V1. We held each rat after surgery at 1% isoflurane for several hours. Shown in panel B is an example of normalized spectrogram from 1 LFP recording session. I want to briefly show what the state transitions we are concerned with look like in the raw LFP signal, as well as in the frequency domain. A single pair of M1 and V1 channels recorded simultaneously produced all data shown on this slide. First, there are many cases where a transition occurs in 2 regions simultaneously. In this case, the power of low-frequency oscillations dropped dramatically in both channels. However, there are also cases where similar transitions in 2 regions are separated by a time delay. And thirdly, we can also identify instances where a transition in one region has no nearby analog in the other. To systematically analyze state relationships and transition synchrony, we first obtained a spectrogram of the LFP from each recording site using the multi-taper method. We then rank order normalized each frequency's power over time and smoothed over frequencies. Next, we wanted to extract a smaller number of informative components from each spectrogram, similar to PCA or SVD. To constrain this computation and discover sets of frequencies that were often present together, we used non-negative matrix factorization, or NMF. Just as in the example on the left, where NMF generates a library of features that reconstructs each input phase when multiplied by its corresponding scores, here on the right, a library of frequency loadings multiplied by a matrix of component scores across time reconstructs each spectrogram with a mean error of 14.8%. To discretize the NMF score vector series into a series of state labels and transitions, we found that we could simply assume that one state corresponded to each NMF component and then label each time point with the state corresponding to the component with the highest normalized power. After filtering out very transient and ambiguous state assignments, this procedure consistently resulted in transitions that matched those that are visually apparent in the spectrogram. The first measure of coupling between channels we considered was transition synchrony. For each transition in both channels, we used this algorithm shown on the left to define a time window tau based on the proximity in time of neighboring transitions, and the transition in question is considered synchronous if a transition occurs in the other channel within this window. Then, the synchrony score assigned to each pair of channels is just a fraction of the total transitions in both that are synchronous. Here are the pairwise transition synchrony results. In this slide and the next 2, the matrices show the values of the coupling measure computed on all channel pairs in the example recording of each type, and the violin plots aggregate across all recordings and contrast within region pairs with between region pairs. Gray squares indicate pairs whose transition synchrony does not surpass values obtained from a null model where each channel was independently shuffled using a Markov chain, according to a Bonferroni-corrected C-test. In total here, 57% of channel pairs in M1-V1 recordings and 80% in pairs of bilateral V1 recordings were significantly synchronized. Also, we can see that the overwhelming majority of pairs had synchrony less than 0.6. Finally, the violin plots show that pairs of channels in the same region were more synchronous on average than pairs that spanned multiple regions. We also computed overall transition synchrony across all channels for both M1-V1 and bilateral V1 recordings. Here we see a CDF of the scores for all transitions compared to the shuffled null models. Again, the result is moderate. They are clearly more synchronous than chance overall, but the scores span a wide range and most are below 0.7. Next, we wanted to look at not just whether different brain regions change state together, but whether the states themselves had a consistent relationship across time. In the limit, this would imply that the activity of multiple channels could be predicted by a single variable. We quantified coupling between vectors of the discrete states using a normalized mutual information measure that ranges from 0 to 1, also known as symmetric uncertainty. These toy examples show that, like plane mutual information, the measure is highest when each series of states is completely predictable from the other, and close to 0 when they are statistically independent from each other. On the right are the example matrices and violin plots of pairwise normalized mutual information. The lack of gray indicates that all pairs had values significantly greater than those produced by the shoveled null model. However, in all plots, we can see that, again, coupling was relatively weak, with most scores below 0.5. And also, again, on the right, coupling is lower for pairs that cross a region boundary. Thirdly, to not rely too strongly on the method we chose to define discrete states, we also measured canonical correlation between the full NMF score matrices of each pair of channels. The results are similar to the last two slides. All pairs had canonical correlation scores greater than those produced by the null model, but coupling varied in strength, and pairs that crossed a region boundary were on average less coupled. Finally, we conducted a PCA analysis on the concatenated NMF scores to confirm that even with apparently weak pairwise coupling between channels, there is global synchrony when considering a larger number of channels. Recall that PCA revealed global dynamics to be low-dimensional based on full concatenated spectrograms in the Hudson et al. Study. After running PCA on the NMF space data, we compared the cumulative explained variance to what we obtained with the null model with independently shuffled channels. In both recording types, global synchrony is clearly present. Many fewer components are needed to reach any variance threshold with the real data. And to the right are the loadings and histograms of some sampled top principal components. Like as seen in the Hudson paper, the loadings are spread across multiple regions, though not identically, and clusters can be identified in the joint histograms. In conclusion, under constant anesthesia, 3 measures show the activity of pairs of cortical sites to be consistently coupled, but with low coupling strength. Synchrony of state transitions, mutual information of discrete states, and canonical correlation of NMF score vectors. Coupling is stronger between sites within each region than between regions, and the dynamics of the full system are far lower dimensional than one would expect if the activity at each site were evolving independently.